Hello everyone. This is a much applied work that I've done during my first year of PhD under the supervision of Professor Frank Nielsen and with my colleagues at Philippe Capital, a credit arbitrage trading company. So the focus on this work is clustering random time series. So to give you the motivations and the context of my work, we have time series from the credit derivatives market, and we have to deal with this kind of data. So it's about 10 years of data, daily data. So that means that you have nearly 3,000 realizations for up to 5,000 of time series. And well, they are very noisy, and you see there are some unpredictable events like the Volkswagen fraud. And what I want to do with that data is clustering. Why? Because we have needs to monitor the quality of data. We have also to have risk indicators, and we want to reduce the dimension even just for computing a variance covariance matrix. Because of the dimensionality, it can be very noisy. So we are aiming at clustering this kind of data. So what is clustering? Clustering is the task of putting objects which are the same in the same group, and such that any 2 points in this group are very similar and points in different groups are much dissimilar. It can be formalized in many ways. For instance, we may want to minimize variance inside a group, and then you can do EM algorithm and stuff like that, much theory, but for the practitioner, it's really boils down to finding a proper relevant distance d between your time series that we will consider random walk time series here. So let's have a look at this time series in practice. Here we have two clusters each time, the red one and the blue one. And if you want to elaborate a distance on this, it's rather tricky, because on this one you say, well, it's correlation, it's a monthetic scaling. But on the first one, it's more the signal shape that is discriminative. And on the last one, which is a real-time series from the market, a machine learner will typically say, well, it's a dynamic time warping. They all look the same in the cluster, but they are just a bit different due to time distortion. And you may want to use this distance, but the problem is that they may have some overlap and things like that, so it doesn't work. So let's go take a different look on this time series. We can consider this time series, so like realization of random variables, and the final this time series in discrete time is just the sum of these realizations. So here I have the n random variables corresponding to the n assets I want to monitor over a time span t. The t days I want to monitor that. And the question that I want to solve is which distance between this time series. This distance has been well studied in information geometry, where you have like Fisher-Rao geodesic distance. But the crux here is that the random variables are dependent, and we want to take this dependence information into account. So we can have a look on a basic distance to grasp what breaks down why we can't use a basic approach like L2 distance between the random variables. So if we take a look at the information in it, we have distribution information like with the mu and the sigmas, and we have correlation information with the rho. The problem in this is that if we consider that we are not correlated, so we may want to discriminate the clusters of time series with the distribution information. It's not that okay because even if they have same distribution, they can be arbitrarily far away. And another remark is that if they are perfectly correlated, once again we may want to discriminate on their distribution, and in this time we have a basic L2 distance on the parameter space of, let's say, Gaussians here. We know that it's not a proper geometry for that. It's more the hyperbolic one which is appropriate. We can see that immediately on this illustration. The three pairs of Gaussians are equidistant. The two green, the two red, and the two blue with this distance. But let's say we can't less discriminate the blue ones from the gray ones because they are much overlapping measure between them. So what we are going to do is to leverage the Sklar theorem, which is well known among financial engineers. And what does this theorem say? It says that if you have a multivariate function of your random variables with univariate marginals, you can write it like a multivariate function of uniform random variables. And this multivariate function is called the copula function. So we can look at it in a more pictorial way. It says like you have, say, on the left, the distribution of your random variables, and you can decompose it under some hypothesis, like continuity, in a unique way. The copula one, so the multivariate function on uniform marginals, and the marginals, the margin, which are P1 and P2. And that's pretty useful because, for example, if you want to compute a correlation on the left scatter plot, if you have outliers, margin distribution infer with the infer dependence, while with this decomposition, we have a proper normalization, let's say. So to do it practically, let's define the copula transform. So it's rather straightforward. You take the CDF, cumulative distribution function of your random variable, you apply to it, and what you come up with is a uniform distribution. So you are doing that for all your variables, and you obtain the coordinates of the copula. This transform has nice properties. If you want, the copula is invariant for up to increasing transform of your random variable. That is to say, you can transform it with a log transform, which is quite common in finance, and you will end up with the same dependence behind it. So it's rather nice property. And to do it in practice, it's even simpler. One can, for example, estimate the CDF and then apply it to the realizations, but I would say it's a rather clumsy way to do it because it's not very robust to noise outliers in the real data. But a more robust way is to use rank statistics, and in fact the construction of the Wells empirical copula. In practice, what you have to do is to sort the realizations by their value and keep the rank. And what will be the uniforms realization? It will be just the normalized rank. So the rank after sorting divided by the length of your vector. And that's how you build a representative, let's say, of the dependence information of your time series. Now we can elaborate a distance on this quite simply. We will have a simple L2 distance. So on a big vector, which is first part the uniform transform, the copula transform, and the second part let's say, the square density of the margins, the PDF of the margins. And you end up with this distance. This distance has nice property. First, it's invariant to increasing transform. Why? Because of the copula transform property, and because of the F divergence properties of the Ellinger distance. The second term is the Ellinger distance. We can see it here. And basically, what I'm just doing is, what is the distance between my two time series? It's the distance on the wall information. That is to say, distance in correlation plus distance in distribution. The first term, which was L2 between the uniform, can be written as 1 minus rho, the Spearman rho, which is the wrong correlation, let's say, robust to outliers, but it's basically just a distance between on the normalized on the copula. And then why do I have a convex combination at the end between the correlation and distribution? That may be a moot point. Well, let's say I really do not know, so I come with something simple which can be computed as a scalar product. That's nice for the practitioner, but also there is some motivation in, let's say we go for the parametric modeling. So you have your density, you can write it as a copula density times the product of the marginals. And if you compute Fisher-Rao geodesic distance between these, it just splits again the dependence information plus distribution information. Sorry. So that's what I propose as a distance between my time series. Now I want to test the efficiency of this approach. So I propose, I will explain why later, this hierarchical block model. So what is it? It's this matrix represents, let's say, the distance between the n elements. So it's a n by n matrix, and it defines nested partitions. So I have a partition, let's say a 4-level partition, the coarser one, which is 4 clusters. Each one is again divided by the first one 2 clusters, and so on and so on. And you end up with your nested partitions. You never observed the left one. What you observed is more the right one, which is identical to the left one up to a partition of your data. And with clustering, you can find an approximation of the left one. But so this model, I can build behind it a generative model. So it can produce time series which are both correlating plus an additive noise, which is let's say Gaussian or Laplacian or student. And I will benchmark this approach against basic distance like distance correlation or L2 distance. And what you can observe, but it's quite natural, is that if you have only clusters of distributions, that is to say time series where I put only distribution information to discriminate between the clusters, you can find it with the proposed distance, but not with the correlation distance, and so on and so on. And yeah, it works quite okay. One is the best score, so you can find these synthetic clusters. But what's more interesting, it's the efficiency on empirical results from the credit derivative market. So what does it represent? On the left, I compute a distance matrix between my assets, and what you can observe it's that it's really hierarchical with nested clusters. For example, you have a 3-level clustering. It's the big one is assets from the US, the medium one is assets from Europe, and the smaller one is assets from Japan, and each is subdivided in the quality credit, high yield, or investment grade, and each one again is subdivided into industries. So the proposed hierarchical model is not that absurd. And then you can test with bootstrapping. That is, you sample in your data. For example, a very naive one is I have my 10 years of time series. I take one trading days variation over 2. I have a left sample. I take the complementary, I have the right sample, and I build my clustering. And with a naive distance, I have very unstable cluster. And that's not a very good property for trading or doing risk, because if you have an indicator which moves for just perturbation noise, it won't be very helpful. So that's what you have if you are using just a L2 between your time series. But with the proposed one, it's much more stable. You find the same clusters, like you are doing a sliding Windows time series, and you may think that if you have moved between your clusters, it's signal and not just pure noise because of a wrong distance or wrong clustering method. But what's more interesting theoretically is that with respect to the proposed model, that is the hierarchical block structure, we can show that this approach is consistent. So what does it mean? It means, let's say you have your n assets, and you can observe more and more data. That is more and more days of prices. And the longer you observe, the more accurate you are. And in fact, you can derive upper bounds. So the proof is in 2 steps. First, you have to notice that your points have to be in a very nice configuration. Let's say that the maximum distance in your cluster is less than the minimum distance between interclusters, that points in the cluster and points outside this cluster. And if you have this, which is, let's say, guaranteed by the model, if your clustering algorithm have the following space-conserving property, what this property means, it means that the distance between your cluster at each step of the clustering remains in the convex hull of the mean base distance, the distance d we built, or any distance, and the maximum distance. If you have this property, many algorithms that are useful for practitioners, like single linkage, average linkage, complete linkage, verifies the property. If you have this property, then you can show consistency in the deterministic case. Some of our clusters, some of our clustering algorithms which are used does not have these properties. For example, the word algorithm, which is used in practice. And the next step is you have to ensure that you have this property in the limit. So what does it mean? It means that what you observe is a matrix with, if you have few data, few contrast, and more data means more contrast. And what you do technically, it's that you obtain concentration bounds on each coefficient, and you have to show that the error on the max error on every coefficient is less than the contrast at the end. And if you have these technical conditions, you can show that in the limits with nice convergence properties, you are consistent. So in practice, correlation converge much faster than distribution, so you will mostly find correlation clusters. And in conclusion, this practical work raises many questions. So a first one I would like to work on is distances on the copula margins, or establish a geometry on copulas, because the most used one is the Gaussian copula, and it's known that it's not very practical. It's not very relevant for financial time series. And also deal with the question. In this talk, I've only presented the univariate case. All time series were univariate, and you have lots of them. It was like in the stock market case, but in fact, in credit derivative, you have multivariate time series. For example, Orange is not just a price each day, it's a term structure of price. This day you can buy insurance against Orange default for 1 year, 3 year, 5 year, 7 year, 10 year. And this has a quite complex structure. So you have information at the intradependence level and information at the interdependence level. And this you could tackle with distance on copulas. So a basic solution is using optimal transport, but I'm sure that Fisher-Rao may help to find efficient one. And another one is using multi-wise dependence information. For now, because I'm wanting to do clustering, I'm stuck with dependence measure between two assets, because the clusterings work by pair, but the thing is that I may need to build dependence characterizing like the copula does, but then it's difficult to exploit this information that characterizes the dependence for k assets at the same time. So thank you very much.
You mentioned the case of multivariate. Have you considered also the situations where you have many components for one point of the time series? Not only one value has been, many other variables has been observed. Do you think?
Higher probability of default. So at time 0, you have 0 probability. At time infinity, you have 1. So it defines a CDF. You can take the derivative, then the square root, and then you end up with Fisher-Rao in infinite dimension. But well, it's a nice approach, but it doesn't make that much sense in practice, because all that you have is only 5 noisy time series and not infinity. But what I have tried to do is for intradependence, that is to say the deformation of your time series, I consider the copula of these 5 time series, and I use for now optimal transport to have a distance between this time series qualifying intradependence, and then I obtain clusters of assets that, let's say, their term structure are deforming on the same manner. And for interdependence, so we know that the copula construction breaks down for multivariate marginals and that there are linkage. But for now, what I'm doing, I take those 2 multivariate vectors, I make a big one, and then what I observe is an empirical copula, and I'm trying to know where it lies on the geodesics between independence, that's the uniform copula, and target dependence. In finance, it's most positive or negative dependence, but you can plug any copula characterizing your target dependence. So that's what I'm doing right now, but I've not that much theory behind it for now.
Thanks. Thank you. Next.